we continue with discussion and description of Newton's laws of motion and its implications. Conservation of momentum of principle. So the momentum is also conserved, and it's a very important rule that prevails under Newton's laws of motion. The momentum of a system remains constant only when the net force acting on it is zero. So if the resultant force is not zero, then the momentum may change, but otherwise it is preserved. So if there is a certain quantity of fluid as represented here by m is the mass of the fluid that is under consideration. It is moving with a certain velocity v, then the mv is its momentum indicated in the given direction, in the direction of velocity. But the momentum of a system, that is this system, for example, if we are considering this, will remain constant if the net force acting on it is zero. The linear momentum is a product of mass and velocity, as we have said, and its direction is direction of velocity. Newton's second law is also expressed as the rate of change of momentum of a body and is equal to the net force that is acting on it. So if I have to write that in mathematical equation, then F is the resultant force, or the net force you may call it, and it is equal to mass into acceleration. As we know, it is again equal to dv by dt into m, and it is equal to d by dt into m into v. We have already written these things, and this particular term can be described as a rate of change of momentum, because we have defined mv as a quantity that is known as momentum. The counterpart of Newton's second law of motion for a rigid body can be expressed as m is equal to I into alpha, where m is the net moment or torque. So when rotation is taking place, then it's not a linear motion, and therefore the notation is slightly different, and we use here m for the moment or the torque for a rotating body, and where I is the inertia or moment of inertia, and alpha is the torque or angular acceleration. So linear acceleration is represented by a rate of change of velocity in the direction. But if it is rotation, then the angular motion takes place, and if angular velocity is, let us say, omega, then d by dt will be representing alpha, the angular acceleration, and of course the remaining terms are its equivalent terms, and momentum equation can be written as dh by dt if we take h as angular momentum. Angular momentum about x-axis. So from the same equation, now this is a vector quantity. So obviously it will have components in all its rectangular direct coordinates directions, x, y, z. So in the axial direction, we can simply put x in the subscript, and the remaining of the equation will remain the same. Mx equal to ix dw d omega x by dt, it will be equal to dhx divided by dt. So wherever in our discussion in these present PowerPoints, if you see any equation that is written, that is referred to the equation given in the book that we are following. We are following the book written by Sanjela, Yunus Sanjela, and I have already stated that for you. So all these numbers are related or refer to the book, and you can see it there. The rate of change of angular momentum of a body is equal to the net torque acting on it. It's very similar to the thing that we consider in a linear motion. The only difference now is that it is being considered in a rotational motion, and rotational motion about axis of rotation. So F has been replaced by M and is known, we call it torque or angular momentum, and then can be written as, instead of F is equal to ma, we write here Ia. I is the inertia and alpha is the rate of acceleration of angular velocity. These are all equivalent terms that is written there and are very similar to the linear equation that I mentioned a little earlier. Choosing a control volume is very important when considering the fluid flow. And of course, any mathematician, any scientist or researcher, he would like to keep things simple so that the equations that are developed, the solution that they are looking for, are also correspondingly easy to solve. So therefore, it's important that how do you choose the control volume. It can be selected as any arbitrary region in space through which fluid flows, and its bounding control surface can be fixed. Either it can be moving or even deforming during flow. Many flow systems involve stationary hardware firmly fixed to a stationary surface, and such systems are best analyzed using fixed control volumes. When analyzing flow systems that are moving or deforming, it is usually more convenient to allow the control volume to move or deform. So control volume also move or deform as the control volume itself is moving or deforming. Now you will recall that I did mention that whenever there is viscosity and external force is applied, then various particles of the fluid flow with different velocities. And because of that, because variation in the velocity in different particles of the same fluid in a given control volume, the deformation takes place. This deformation is a resultant effect of viscosity. In deforming control volume, part of the control surface moves relative to the other parts, to part of the control surface. And some of the examples in choosing the control volume are represented here. For example, for a fixed control volume, you can see here that if there is a fluid flow passing through a pipe that is fixed, then we have to choose a fixed control volume, and in which the fluid is passing through, entering from the left and exiting from the nozzle. But if, for an example where the control volume itself is also moving, we can easily consider a simple example of flight of an aeroplane, whereas when the plane is flying, and if we choose the control volume to be the area that encompass or include the whole plane, then you can see that this is what we should use, and it should remain convenient for analysis of flow fields and forces that will be generated because of these two forces. And similarly, if there is an engine or cylinder is moving and gases are inside, then as the cylinder moves in, There is deformation because the viscosity is changing, because the density is changing, and so on, and therefore the deformation control volumes. Here is an example in which we can choose it in this way.